if we take R2, we remove the point origin, that is we have our x, either you call it complex plane or R2, from there remove origin, then it is obvious that in fact x is pathwise connected. So, in fact you take say Z1, Z2, so we join Z1 with origin, suppose Z1, Z2 or such that 0 is on the line segment joining Z1 and Z2, then we have a straight line path, or it can be then our origin here, that is not in the domain, but origin 0 0 does not belongs to capital X. That means this path, the line segment, this we can give a path t goes to 1 minus t times Z1 plus t times Z2, but this will not be a function, that is we cannot take this as f of t, because for some t you will get f of t is 0. So, it will not be a function from closed interval 0 1 2 R2 difference origin. So, we have to avoid passing through origin. So, just take any other element, say Z3, which is not on this straight line. Now, we can join Z3 not equal to origin. So, there is a path joining Z1 and Z3 and also a path joining, this path will not, without this select the path Z1 to say Z3 and Z3 to Z2 such that origin 0 is not here. So, this we can prove for any Z1 Z2. So, hence R2 difference origin is pathwise connected. In fact, you can prove that not only one point, if we remove any finite number of points, it is easy to see that R2 difference, that finite number of points will remain pathwise connected. In fact, if we remove capital A, a countable subset of R2, then also we can prove that R2 difference A is pathwise connected. We will not see the proof here. So, our main interest is to see that in R2 every open set is open and connected. Open connected set is not just open, open and connected set is pathwise connected. So, we have, for example, this, take the unit circle. So, we call it capital X is S1, set of all order pair x1, x2 in R2 such that it is a circle, center at origin, radius 1, such that x1 square plus x2 square equal to 1. Only points on the boundary circle. So, this is our S1. So, in fact geometrically it is now 0 0 is not here. If we take any point x and any y, we can find a closed interval a comma b in R and a continuous function from closed interval a b to S1. Say S1, in fact we can define a continuous function from closed interval a b to R2, but rest in such a way that the range of closed interval a comma b should be a subset of S1. That is, in this sense it is a function from closed a b to S1 such that function is continuous and at 0 it takes a value, the first point x instead of 0 here a, such that f at a x, f at b equal to y. It is not always necessary that you should get a continuous function from closed interval 0 1 to whatever the topological space. In fact we have seen that using there is a homeomorphism between closed a b and closed 0 1. So, we have already, if there is a continuous function from closed a b to some given topological x having that property, we can also get a function from 0 1 to closed a b, then we can get the composite function. So, this is pathwise, one can easily prove that it is pathwise connected. For example, we are familiar that if we define f of t equal to order pair cos t comma sin t, or the so called in complex plane if we write e power I t, then when t equal to 0 will be at cos 0, when t equal to 0, t goes to cos 0 comma sin 0, that is 1 comma 0. So, we will be at x is coordinate 1, y coordinate 0, we are at 0, then we will make a, when at pi by 2, when it t is pi by 2, so t is pi by 2 means t goes to, that is 0 goes to 1 comma 0 f of 0, pi by 2 goes to, that is when t is pi by 2 f of pi by 2 is what, cos pi by 2 comma sin pi by 2, this but cos this is 0, sin 90, pi by 2 is 1. So, this is our point 1 comma 0. So, like that we know that when t varies from 0 to pi will be at minus 1 comma 0, and again you will come back when t equal to 2 pi. So, we can in general, that is what, you give any x y in the unit circle, we can always find geometrically, this is a, we can find a curve joining x and y, that is part of the circle. So, S1 is pathwise connected. In fact, it is also easy to see that R2 to S1, we can define a map in a natural way, define say f from R2 to S1 as f of an element x, again we will take care that we want to write x divided by length. So, length should not be 0, so that means x should not be 0, remove the origin, order pair. So, 0 0 will remove. We know that this is pathwise connected, we can prove that this function is continuous. Also it is easy to prove that continuous image of a pathwise connected space is pathwise connected. So, that is here the norm x is norm of order pair x1 x2, that is the usual length, order pair x1 x2, that is length of the vector x, positive root of x1 square plus x2 square. I mean, in that case continuous image of this pathwise connected space is S1. So, and hence S1 is pathwise connected. Also one can give a direct proof. So, and in connected spaces we will just state some of the important using the interval. See, just we know that closed interval is connected. For that matter, any interval in R is connected. So, in particular closed interval is connected, and f from closed interval a comma b, we will assume that a comma b belongs to R, a less than b, and this function is continuous. So, what is the properties of continuous function? This is connected, f connect close a b to or f is continuous, closed a b is a connected subspace of R, is a connected subspace, here one and the same, subspace or subset. F implies the image, continuous image of a connected space is connected. So, f of close a b is connected, but what are the connected set in R? We know that intervals are the only connected set, but this imply close connected subset of the real line R, imply is a connected subset of the real line R. This imply closed in the f of the range is an interval. So, now consider the case, suppose even it may be a constant function. So, that will be continuous singleton, the image, the range is singleton, then it is connected. Suppose the function is not a constant function, and further suppose f of a not equal to f of b, then either, so we will have then either f of a strictly less than f of b or other way, that is f of b is strictly less than f of a. The case 1 is f of a is strictly less than f of b. Now, that means f of a is already in the range, belongs to f of closed interval a comma b, f of b also in the closed interval a comma b. suppose this is some interval, let us call J. So, J is an interval, and so this now J is an interval. What is the prop? So, we have the set. So, consider any element C. So, now that is we are taking C a point between f of A and f of B. So, mean that is in the, if C equal to f of A mean f of A is C. So, we will assume that C is in the open interval. So, that means that is C belongs to, so it is a point between f of A and f of B. Now, f of A, f of B belongs to J. J is an interval, will imply all the points between C and f of A will be also in J. So, this will imply C belongs to J, but J equal to f of closed interval A comma B, that imply C belongs to f of closed interval A comma B. This implies there exists x belongs to closed interval A B such that f at x equal to C. That is, if C is a point between f of A and f of B, then we can find an x in closed A B such that f of x equal to C. So, the same thing will work in case if it is f of B less than f of A. What we need is again C lies between this interval between f of B and f of A, and f of B, f of A belongs to J. J is an interval. So, that will imply C will belongs to J, that means again we will get an x having this property. This is the celebrated, in some sense it is a intermediate value theorem. So, what is intermediate value theorem is just it is an application of continuous image of a connected set is connected. Yeah. So that is, I mean we are not again writing. So, this is a well known result which has many applications. Now, just let us see if the spaces are not connected. If it is connected, so what is, see there cannot be a, see there may be a subset which may be x may be connected, some subset may be connected, some subsets may not be, need not be in general connected. But if so, consider say for example, consider the say open interval 0, 1 union open interval 2, 3, say open interval 4, say 5. So, the union of all these three set forms X, that is open interval 0, 1 union open interval 2, 3 union open interval 4, 5. So, it is clear there, if it is take the union of open 0, 1 union 2, 3 is our A, non-empty open subset of X, but if we take intersection with X we will get the same set. So, these are all, A is open 0 1 union 2 comma 3, a open set open in X, and capital B 4 comma open interval 4 5 again open in X. What is open? We should get a open set in the whole space intersect with the subspace. Here G itself open. The subspace here is X. Here X is in fact X itself open. So, if G is open means G intersection X will be open in X. In fact, it is open in the whole space. So, A and B are non-empty open sets and X equal to A union B and they are disjoint, A intersection B is empty. So, X is disconnected, not a connected space. So, now take an element say X belongs to or say open interval 0 comma 1. So, then this open interval 0 1 is a connected, we know that intervals are connected. So, open 0 1 is a connected set subset of power X. Open 0 1 is a connected set containing X. So, now we will find an say a R small enough such that even let us say X minus R, X plus R, then this open interval X minus R to X plus R is also a connected set. See, let us say that we can find R sufficiently small, find R greater than 0 such that open interval X minus R, X plus R completely contained in fact X open 0 1 is a open set. We have proved that each point is an interior point, there will exist on R having this property, and in fact here we can find R such that this is a subset but not equal. I mean that is, so any open set without the radius should be less than here this distance between x and 1 and 0 and x in this case. So, find this, then this is also a connected set containing x. So, there may be in particular even singleton x, this is connected subset of capital X containing the point, the given started point, connected subset of X containing the particular X. We have fixed one X in the open interval 0 1. So, like that there may be any number of infinite number of open set containing the point X, any small interval containing X, they are all open set, including singleton X is also a connected subset of X containing X is also connected. So, there are many connected sets containing that particular point X. So, among these what is the question is what is the largest or say maximal, largest connected subset of what is the larger connected subset of our topological space X is the given space X containing X. So, whether question is in general if you are given a topological space X and a point X in X, first question is yes, we can always find a connected set containing X, singleton X is there. Then what we will do is collect, so let us say X script Ax is set of all C subset of X such that C is connected, C connected and it is a connected set containing C. We are collecting all those connected subsets of X such that that set X contains C, X belongs to C. Then what about union? So, will all X is everywhere. So, this collection is such that intersection C belongs to that script A suffix X is non-empty, because if we take an set C member of this collection then X is there. So, this is X belongs to C. So, each is connected, it has a common point, then we have seen that that union is connected. So, then this will imply the union. So, this will imply union of C belongs to script A suffix X is connected. So, in fact now you take any connected set, suppose A is connected, A connected and it is a connected set containing X, then A should be a member of script A suffix X. So, that means A will be a subset of this connected set. So, let us say this is our M suffix X. So, in fact this is all other connected subsets containing X will be a subset of Mx, that is this is the largest connected set containing X. In fact we have proved that you give any topological space we can always find the largest or say maximal connected set containing X. So, for example in this case what are our maximal? So, now you take any X, this open interval 0 1, say we call it say M1, this set M2 open interval 2 3 M2, open interval 4 3 M3. Now all these sets they are all maximal connected sets. So, these are all maximal connected set containing which point? If we take any point in open 0 1, then the same M1 is in fact the maximal connected set containing X, it will be unique. So, similarly if we take any point in open interval 2 comma 3, same open 2 comma 3 is the maximal connected set containing points of open interval 2 comma 3, similarly this. In fact, so in fact we can prove that in this case the each maximal connected set will say that they are all components. This connected M1 in this case M1 M2 are called components when we say component means we mean connected component, or say connected components of capital X. So, they are all connected components of X, and one can write capital X as a union of such C, where C a component. So, also suppose let us say M1 component, that means M1 is a maximal connected set containing some point. So, it is a maximal connected set and M2 is maximal connected set. And we let us assume that suppose the intersection is non-empty. Suppose what we have is M1 maximal connected set containing some point x1, that M2 another maximal connected set, then what will happen? There is a common point, and that means this will imply M1 connected, M2 connected, intersection is non-empty, imply M1 union M2 is connected. So, it will be a connected set containing, so if you take a point, so we told that x1 belongs to M1, it is a connected set containing M1, then this will be also a connected set containing the same x1, x1 is a belongs to M1, then M1 is maximal connected set containing x1, then this will imply this union will be a subset of M1. So, that means M1 here M2 is subset of M1 union M2, which is subset of M1. Similarly, M1 is subset of M1 union M2, so which is again the same way we will, this is also a connected subset containing points in M2. So, this same way we can prove that it is M2, that is M2 subset of M1 and M1 subset of M2, that is meaning is once M1 M2 are components implies one M1 intersection M2 may be empty, yeah. If they are non-empty mean they are identical. So, or M1 equal to M2, either they are identical or disjoint. So, that way X can be written as union of components such that they are pairwise disjoint. In fact, other way of realizing this maximal connected set is in the following way. For X topological space, consider X y belongs to X, define a relation, say X, read X is related to Y, if and only if there exists a connected subset containing x y. So, x comma y. So, x related to y means we can find a say connected subset of the topological space x y such that x y belongs to that connected set. Then we say that x is related to y. So, this is we can prove that this is an equivalent relation like x is related to x, because singleton x is connected set containing x and x. So, x related to y mean Ex, there is a connected set containing xy, it also contain yx. So, x related to y. If there is a connected set containing xy, another connected set containing y and z, then y is common, that means the union will be a connected set containing y and z, that means x is related to z. If x related to y, y related to z, then that imply x related to z. So, this will be an equivalent relation, and hence this will partition this relation. We have x that will partition the set into disjoint, in fact not disjoint equivalent classes. Each is a equivalent class, in fact that is equivalent class is nothing but our maximal connected sets. Okay. Yeah. Now just we will introduce the concept called compact quickly, and then see how in a natural way we will come across such sets in a topological space. So, we will now we will introduce the other important concept, namely here what is called a compact. The name itself indicates something very compact, when it is something we identify like a small. Compact subset, what do you mean by a compact subset of a topological space? Compact subset of a topological space. So, here we have a topological space x tau. So, x tau topological space given. So, either we can first introduce the concept for the topology. When you say a topological space is compact, then a subset or a subset y of x is compact mean the restricted topology, that is tau will induce a topology tau y on y, and if this topological space is compact mean the subset y is compact. So, we will define the concept for a subset. So, in particular the x is also a subset. So, let us define when we say a subset of a topological space is compact. So, we are a subset. So, definition is a subset say capital Y of a topological, say this will write for topological space, a subset Y of a topological space x tau is said to be a compact, either we can say compact subset or compact subspace. So, let us just say that is said to be a compact subset of capital X, X mean with the topology tau, if and only if, that means it satisfies the condition, namely see topology mean what we have a collection of open sets. they are all called neighborhoods. So, if we can cover this subset by a collection of open sets in X. So, if and only if whenever say script A is a subcollection of tau, whenever is a collection of open sets in capital X, that means script A is a subcollection of tau such that this will cover the set Y, meaning is Y is a subset of all such union. A comes from script A. See what is the obvious such, then this script A is called an open cover for Y. So, if we take script A equal to tau, then union A belongs to tau will be the whole space X and Y is subset of X. So, in particular always you will get a open cover, but what is this tau in general contains, it will contain a large number of open sets. So, if you want to say the set Y is compact, mean it is something like if some work can be done by a group of, by a large, in some sense we understand what we mean by large collection of persons. Suppose whenever you can get that work done by a collection of large person, then here is a person come and says that in some sense we understand what is a smaller collection, we understand intuitively, then the same work can be done from this large number of person. We can identify some person who are very efficient in some sense. Now, these finitely many persons from that large collection, this finitely is small enough, so that will be sufficient to complete the work. So, in this sense here script A is a collection of open sets which covers Y. This collection may be large, then whenever script A is a collection of open set having this property, then there exists a finite subcollection, that means there exists a finite subset or we say subcollection, say script F, which is a finite subset of script A, such that now this finite subcollection will do the same job, that means it will covers the whole the Y, such that Y is also a subset of union of A belongs to script F. In general we assume that script F is non-empty and finite mean, see script F will be of the type some F1, say F2, Fn, or if you use the notation A, let us say A1, A2, An, this will be a subcollection of script A and Y will be subset is nothing but contained in 1 to n, Y is subset of 1 to n. That case script f is here, script f is some finite, there exists at least one. Whenever script A is a collection of open set which covers y, then from that we can extract a finite subcollection which covers y, then we say that the topological space y is a compact subset of x. In particular, if x itself compact, then we say that the topological space x tau is compact. That case, instead of naturally x is subset of the union, every A is subset of x, then x will become the whole union of A in script A. So what are the natural examples of compact topological spaces? See, what are the one thing is capital X itself, say a given topological space, capital X tau, any topological space, any given topological space, take a finite subset. Suppose for y, even if it is non-empty, say x1, x2, xn, a finite subset of x. So, I mean then also now what will happen if there is a collection of open sets containing, that means satisfying this condition. Suppose script A is a collection of open sets in X such that this, that is a cover mean y is subset of union A is in script A. Now what is our y? Only it is x1 comma x2 comma xn. So now x1 is in y will imply x1 is in the union. So hence there will exist at least one A1 from script A containing x1. Similarly x2 will belongs to y, so there will exist at least one A2. There may be more than one such sets such that say A2 contain x2, another say A3 contains x2, then you just fix any one set. So we will get at least one, that set is fixed, it will contain A2. x2 will belongs to A2, that is A2 contains x2. Also it is possible that A1 equal to A2, we do not say that they are disjoint. I mean when we just counting here it is A1 comma A2 An. So we do not say they are all distinct. So then, so that is, then for each I we will get, so for one A1 from script A, 2 there is an A2 from script A, for n there is an An from script A, such that here x1 belongs to A1, x2 belongs to A2 and so on, xn belongs to An. Then what is the conclusion is, so we have, so there exists a subcollection, there exists F which is A1, A2, An, a finite subcollection of script A, this is finite, such that y is also a subset of that E, the finite union of that subcollection. So, Y is subset of A1 union A2 union AN. So, that is whenever script A is a collection of open set which covers Y, then from that we can extract a finite subcollection such that that finite subcollection will cover Y. So, hence by definition this will imply Y is compact. Okay. Yeah. So, we will continue in the next lecture.